Hi everyone! Today we're going to look at a novel way to scale up computation. So previously we looked at how to scale up computation using a cluster of machines, such as using Hadoop and Spark. And we'll look at today that maybe that's not necessarily all the time. So we will look at a novel way to do that using your own computer. So previously you looked at how to scale up computation using Hadoop and Spark, or using cloud services like Amazon Web Services or Azure. So one question often people have is when should they use it, or when should they not use it? So in this video, I'm going to tell you a little bit about a project that was originally developed at Georgia Tech, and it's using memory mapping, or loosely you can think of it as virtual memory to scale up computation. And it was a project that's led by Jerry Lin, who was a computer science undergraduate student at Georgia Tech, and now he just started his PhD at Stanford. The problem that MMap look at is to figure out, is it always necessary to use a computer cluster to do graph computation? So the main reason to look at this is because using a computer cluster, it often involves a steep learning curve. So it's not as something as easy as just switching a language. You also need to learn about the hardware characteristics, how to allocate enough RAM, and so on. And also there's a cost in using a computer cluster. So there's the hardware cost potentially, and also the cost of acquiring people who know those skills. And more importantly is that for smaller graphs, such as graphs that are maybe at the million scale, is actually overkill. Because for such graphs, it actually may only be a couple hundred megabytes. So it can easily fit in everyday's computer these days. So these observations got a lot of researchers thinking and said, well, so if we don't use a cluster, what can we do? So there was originally at 2012 where GraphG, one of the first project that look into this. And they say, well, maybe we can use a single computer, so a single machine, as in some like your laptop or your desktop computer, and try to figure out how much computation power they can really squeeze it out from the machine. So GraphG is the very first project, and also there's follow-up work like TurboGrafx, aka 2013, that also look at similar problem and try to speed up a computation even further. And what they have in common is that both of them would use sophisticated data structure to help squeeze the whole graph into memory, or part of them. Because often when you have a larger graph, let's say tens of gigabytes, while your computer only have 4 to 8 gigabytes, then there's a question of how do you fit the right portion of your data into memory. And also because of that, then these approaches need to do explicit memory management. So that means they need to figure out when to load data into memory and when to offload data from memory that are no longer needed. But what that got us thinking is that, well, so it seems like there's a cost to pay. You need to design data structure, you need to do the memory management. So can we do less? So meaning, can we do less memory management? Can we use any standard data structure so that we can get the same or maybe even better performance? So that means, can we use automatic memory management techniques, for example? So that got us thinking. So we're saying that if a graph is large, so usually that means there are a lot of graph edges. So for a billion edge graph, the edge list, for example, can be up to tens or hundreds of gigabytes. So it will not fit into the main memory of a laptop or a desktop computer. So can we say, using automatic memory management techniques to automatically determine which part of this edge list is needed during computation, and have that part automatically be mapped or be uploaded to the physical memory, so which could be about 8 gigabytes for a commodity machine. And also similarly, can we automatically unmap or unload data that no longer needed? So this is actually very similar to what other approaches like GraphG or TurboGrafx was doing, but instead they're doing this manually. So that means in their memory management technique, they determine when to map and when to unmap data from the main memory. The main idea with the leverage is that, well, it seems like this is something that modern day operating system is already able to do. So specifically, this is exactly what happened in the virtual memory system. So virtual memory has been around for a long time, as long as there was an operating system, because there's always never enough RAM. So that means when you have an application that requires a lot of memory, and you run multiple applications like that, the operating system needs to determine when something's really needed and have that things that's really needed and put it into main memory. And for the application that's not really needed, then they will offload it from memory. So that's really what our virtual memory system is doing. So that means what if we directly use this virtual memory system and instead use it to scale computation, specifically to automatically determine which part of the data set is needed and which part is not? Then how much of scalability can we get? And actually, this is all the main idea that the MMap project is leveraging. So that also means that it's actually not only conceptually really simple, implementation-wise is also extremely simple. So we're going to look at an example of how to apply this simple idea to scale up PageRank, for example. So from the graph analytics video, you saw how we do PageRank using the very scalable power iteration method, where we compute a PageRank vector using a series of matrix vector multiplication. So that means in this graph, the data structure or the part of data that's taking really a lot of space is the graph edges, which is a matrix B here. And it's often very sparse for a scale-free network. So an alternative view for the PageRank algorithm is shown here. So this is actually a figure that we take from the MMap publication. And here, in this alternative formula, we are showing the same thing. It's just using different symbols. So that means in previous screen, we see the matrix B, and here we are using the notation E. So it's the same thing. But on this screen, we are explicitly spelling out the data structure that we're using to store the data. So for the graph E here, so instead of storing at a matrix, which is not really efficient, space efficient, we store it in an edge list. So which also means that the edge list is what is really taking a lot of space. And which also means the edge list file is what we're going to map into the main memory using the memory mapping technique. So that means we're fitting this edge list into the virtual memory of the operating system. So that is all we're doing, and that's all we need to do. So how well does MMap work? So we did a series of experiments to compare MMap with other techniques like GraphG and TurboGraph. And we use different data sets and also run different algorithms on these graph data sets. For example, we're looking at a chart where we're looking at the runtime that's for algorithm run on the LiveJournal graph, which is 17 million edges. So 70 million may sound pretty high, but in fact, the edge list is only about 500 megabytes on disk. So at the top, we are looking at the speed of running 10 iterations of PageRank on this graph. So for MMap, it takes only 3.3 seconds, while for other techniques like GraphG, it takes about 54 seconds, and for TurboGraph, 6.3 seconds. So it's a dramatic increase over GraphG. And also notice that GraphG is actually a pretty big library, has about 8,000 lines of code. While for MMap, because the implementation is really simple, so we only need to do one function call to fit the edge list file into main memory. So the actual number of lines of code is only about low 100. And similarly, we look at the connected component algorithm. The result is shown at below. Where similarly, MMap is also the fastest, only taking 2 seconds to find all the connected components in the graph. So for this LiveJournal graph, 70 million edge graph, actually the whole graph data fit in memory. So for the case where the graph does not fit in memory, as in the Yahoo web graph, which has 6.6 billion edges, then we also see very good results. For example, for MMap, it takes about 579 seconds to run 3 iterations of PageRank, while it takes much longer for GraphG. So for MMap, the timing is pretty similar to TurboGraph. So you might ask, well, so it's not a big increase or big speed up. But notice that for this other library, you will need to do explicit memory management. And also implementation-wise, MMap is much simpler. So that means you can essentially implement different kind of algorithm that may not be provided by GraphG or TurboGraph. And also for other queries, such as finding the one-step neighbor of a node in a graph, we also see that MMap is significantly faster than another approach like TurboGraph. where for MMap it takes only 3.3 milliseconds. For TurboGrafx, it takes 154 milliseconds. So we may ask why memory mapping works so well. The main reason is actually leveraging the characteristics of virtual memory systems. So for example, virtual memory system has something called read-ahead paging. So that means to preemptively load part of a file that the system thinks would be needed into memory preemptively. So it worked really great for our case where we have the graph edges, and if we're starting to load from the beginning, then the operating system would say, oh, you probably may need to use the rest of the edges too, so let me preemptively load those into memory as well. And also, virtual memory system would like to often cache things that are used a lot into main memory for as long as possible. So that is the least recent used memory management technique. And that translates into keeping the high degree of information in the memory system. So that's also a very natural and desirable thing, because often high degree nodes in the graph is also where the algorithm often access. So that means that information is already cached. So that's as if they're already in memory all the time. And lastly, all these memory management operations are actually highly optimized because virtual memory has been around for a very long time. And also, we don't need to explicitly manage memory. That means it saves us a lot of bookkeeping. Since virtual memory is such a ubiquitous technique, it's available on almost all modern systems and also hardware as well. So that means if you want to do memory mapping on mobile devices like an iPad, you can also do that. And the speed is also very impressive. So here, what you're looking at here is that we compare the speed of running an algorithm on iPad mini versus a MacBook Pro. So you'll see that we can handle graphs as large as 272 million edges. And the speed is roughly about 5 times slower. So not a lot. And also you notice that iPad or like mobile devices these days have become increasingly powerful. So that means the gap will be even closer as time passes. So we also extend our investigation to look at how memory mapping might apply, how well it works for a machine learning algorithm. For example, on the left here, we're looking at how memory mapping can scale with data size. So horizontal axis is the data size on disk, and vertical axis is runtime. So we're looking at the runtime of the logistic regression algorithm. Specifically, we're using LBFGS as the optimization routine. And here the blue line showing you how well M3 scales. So it's roughly linear. So that means even after the memory exceeds the memory size, which is 32 gig, it can still work all the way up to about 200 gigabytes. And the scale is almost linear, so which is fantastic. And similarly, we look at how M3 compared with Spark, 4-node Spark and 8-node Spark. So in orange is 8-node Spark, and in light orange is 4-node Spark. So we note that M3 speed is pretty comparable to 8-node Spark and significantly faster for 4-node Spark. If you want to learn a lot more about the memory project, I highly encourage you to go to our project website to take a look at the publication and also download the dataset to try it out yourself. In this video, we look at a novel way to scale up computation where you can just use your computer, and it's based on virtual memory or memory mapping.